Given an array of distinct integers nums and an integer target, return a list of unique combinations of nums where the chosen numbers sum up to the target. The combinations may be returned in any order. An integer from nums may be chosen an unlimited number of times. Pay attention to that. Two combinations are unique if the frequency of at least one of the chosen integers is different. Now these examples should drive it home. So we have these numbers and then we have a target of 7. What combination of numbers, regardless of how often or how on often, how not often they are combined, give us 7. So to get 7, the only way to get 7 for this array is to take 2 twice and add it to 3. That's 4. That's 3, 7. And to take 7. That's another subset that works in this array. And then for 6, if the target was 6 and we had these numbers, we can use 2 3 times. We can use 2 and 4, 4 and 2. And then we can use 6 once. Okay, so that's that about that. Now for the solution, again, it's a dynamic programming problem, so we're going to use past solutions to find the final answer. And so we have this number, right? Walk with me, 2 3 and 4, target of 6. Now just intuitively in my head, I'm thinking, okay, how can I get to 6? Just in my head, I think 2 3 times. I think we literally just looked at this. Okay, no, it's just similar, but 2 3 times, 3 twice, and 4 and 2. Right, that should do it. But how would we do it programmatically? So the first thing we're going to do is initialize this lookup table, and what it represents is we're increasing the target systematically from 0 to 6 and finding the best solution along the way. And each of these best solutions contribute to finding the best solution, following best solution until we get to the target we're looking for. So what does that look like in code? So we initialize this 3-dimensional array, seed it with a single array, and then we're looping through and adding empty arrays for each thing in there, for each item from 1, right? From 1 downwards, and because 0 is already set. Then in 0, we're pushing 1 empty array. Okay, and why are we doing that? We're seeding that because 0 represents, okay, if our target was 0, what subset would we get that would lead to that would sum up to that? And the answer is the empty subset, right? Which is the first thing. Okay, so selecting no number, the empty subset. And now for 1, if the target was 1, right? So now we're looping in here, and what's going on is for each of these targets, right, up until 6, we're gonna loop through every single number, right, for each of them, right, and see how we can best combine them at each step. So in this case, our I is 1, so we're evaluating 1. If the target were 1 and we had these numbers, how would they work? So if J starts off at 0, which is the first thing here, is a cursor loop. J is our cursor looping through nums, and 2 does not fit in 1, right? So that doesn't go. We don't do that in there. 3, neither does 3, neither does 4. So 1 gets nothing, basically. And that's because this condition here never triggers, right? They don't fit inside 1, right? 2, 3, or 4 don't fit inside 1. And you can see here we're looping up until target for 1, up until target. And then for each of those, we are looping through the numbers. We're using J as a cursor through the numbers and checking if they fit. So that in that instance, they didn't fit. Now we've come to 2. And then we're going to reset our J cursor again back to 0. And we're checking if 2 fits inside of 2, which it does. It actually does. And now what does that mean? If we were to take 2 into a sum to find out what we'll add it to get, like, 2 plus what gives you 2? 2 plus 0. So basically, we're going to pick the best thing from 0, add it to 2. The best thing from 0 to this empty array, we're going to append 2 to it, and that's how we get this situation where, okay, if the target were 2, 2 would fit in. And it looks like this in code. So we're looking at I minus nums indexed at J. So remember, in J is 0 right now, and nums indexed at 0 is 2, is the first thing here. And I, in this case, I became 2. So if the target were 2, right, we would pick, assuming we added 2 plus what gives you the target. That's what this is calculating. This is computing. And then so we're going to loop through that and append 2 to it. Okay, I hope that is clear. And again, this pattern follows through practically all dynamic programming problems, particularly the iterative solutions to them. And so that's how we end up getting 2, right? Now I'll explain what this sort is for, but we end up pushing it in here, right? I'm in building our solution, but you'll soon see what sort is for by the time we're done stepping through this problem, and what this is for as well. Okay? And so we move on. Will 3 fit inside 2? No, it won't. It's bigger than 2. So this is not gonna let anything happen there. Neither will 4. So then we're done with that case. We've gone through everything here for this target. So we move on to the next one, 3. So with a target of 3, 2 would actually fit. If we start again, 2 would fit in 3. However, if you were to pick 2, what combination would give you 3? 1. And then we know that there is no combination that would fit inside 1. And because of that, we end up not 2 is disqualified, right? 2 doesn't fit. And you can think of it in a way, okay, how can I get, if the target were 3, what combination would give me 3? Nothing would, right? Because, I mean, evaluating 2 first, bear with me. Evaluating 2 first. 2 and what would give you 3 if the target were 3? And there is nothing else in the array to combine to get to 3 if you have picked 2. And because of that, we don't pick 2. So despite the fact that 2 does fit, right? 2 here is 2, j here returns 2, is indeed less than 3. However, when we come in here, 3, because I is 3, minus nums index j minus 2, gives us dp of 1. And at position 1, when the target was 1, nothing worked, right? And because nothing worked, 2 therefore doesn't work. But in the other case, 3, when you put 3 in there, 3 and what gives you 3, right? 3 and 0, and there was something here. So in that case, you append 3 to that, you get this 3 in there, and move on. Now we're still yet to look at sort, when sort comes in, right? Right now we're just focusing on this, right, this operation, but bear with me. And then lastly, all right, we're evaluating 4. Now 4 doesn't fit in 3, so we just move on. Now at 4, something interesting stuff starts to happen. So we index at j, right? The first j starts again from 0. So we have 2. And now 2 is less than 4, right? 2 would fit in 4. So but if you were to pick 2 and what would give you 4? 2 and 2. So you subtract that in here, right? So 4 minus 2 here, nums index at j at 0 is 2. And that gives you 2. So you pick the best thing from 2, which is 2. Add 2 again to it, and you get this first value. Next, we're going to check 3. So in the case of 3 and what would give you 4? You subtract, you come here again. 3 is less than 4, absolutely. But 4 minus 3, I is 4, nums index at 1 is 3. So 4 minus 3 is dp at 1. And at dp at 1, there was no good solution. There's nothing in this array that sums up to a target of 1. And so therefore 3 is disqualified. On the other hand, 4 works because 4 minus 4 is 0, and there is something, right? There's an empty set that works with 4, so just append that, and then for 4 we get these values, and we're done. We've looked through everything here, so it's time to move on to 5. Now for 5, we start off with 2. 5 minus 2 is 3. So what was the best thing at 3? 3 itself, so add it to 2. Aha, and this is when it's sorted. You notice it's sorted from 2 to 3. It's not 3 2, it's 2 3. It's always sorted from lowest to highest. And there's a reason. When we come to 3, 5 minus 3 is 2. So we get 3 2 again, right? But again, we've sorted it out. We sorted it, so we're not going to include it. We don't add it. We don't add it because we sorted it. So prior, just now, we got 2 and 3. And then we were evaluating 3 next, and we got 2 again. So because we've seen it before, it was sorted, everything was sorted. So 3 2 became 2 3 again. And then we checked, oh, actually, I've stored this before. I've stored 2 3 before, so don't push it again. All right, so that's why it's not pushed again anymore. And then lastly, we check 4. 5 minus 4 is 1. Again, there's no combination here that gives us 1. And so therefore 4 is disqualified. That gives us a target of 1. So 4 doesn't work, right? It doesn't have a companion. Now we'll move on to 6. 6, we start off again from the beginning here. J starts off again from 0. I is now 6. 6 minus 2, right? Which is I here. I is 6. Nums index at J evaluates to 2 because it started again from 0. And that we get 4. So for each thing we've seen in for, that's what previous is. We concatenate it, we sort it to see if we've seen it before. In this case, we're concatenating 2 and 2. That's how I get 3 2s. And then we check, have we seen this before? No, it's the first time. We're just, J is still 0. It's the first time we're seeing this. So just push it in there. So that's like 2 2 2 goes in there like straight away. Next, for 4, we check, have we seen it before? Nope. We're still at J of 2 for 6, don't forget. So 2 and 4 come to combine and get together, give us 2 4. And we're done. We've seen everything that is under 4. The best solutions under the target of 4. And so we move on to 3. So 6 minus 3 is an I of 6. Nums index at J evaluates to 3, 6 minus 3. So we get the best thing out of 3. And we haven't seen it before. So this branch lets us proceed. We haven't seen it before under 6. And so we get 3 and 3. And lastly, we come down to 4. Like the last thing, we move from 2 to 3 to 4. 6 minus 4 is 2. There's something there. So we have 2 and 4. However, we've seen this before. 2 and 4 exists, right? Right. Again, they're all sorted from lowest to highest. So it would be 2 and 4. It wouldn't be 4 and 2. So this doesn't let it go through. And that's why we don't add that. And we're done. We're done processing every single thing. And we're done. So let's look at time complexity. Time complexity is complex, like to put it mildly. So we have this thing going on here, right? So where T is the target, right? Target, whatever target, total target, N is the length of numbers, the total length of the number array, and S is T divided by M. So the target divided by M, where M is the minimum value, it's the smallest value in numbers. And this is because O of T, O of N, and O of S time is taken by the first, second, and third loop respectively. Moreover, S log S is taken by the sorting. So this is O of T, looping through target, O of N, looping through nums, and looping through this thing in here, right? The factor of this, S, which is the target divided by the minimum value. And the sorting takes X log S. So complex time complexity, but it is to be expected. It's a dynamic program. And then the space complexity for the solution is T by N by C, where C is the average size of combinations in here. Okay, and that's all there is to this problem. Cheers.